Information that's presented in class, goes mostly, or just it's hard to keep focus. It's hard to keep attention to things in class, and that's usually okay because you have the book, right, that you can fall back on, or you have the videos or whatever else. So on the one hand, I'm kind of torn because on the one hand, I should follow along the book strictly, so in case none of the information makes it through. But the way the chemical reactions are presented in the book, I don't like at all. And so this is where I'm going to deviate, kind of dramatically, from the book's presentation significantly. And so if you could just try to pay attention and try to get down as much information as possible, that would be very helpful. Otherwise, you aren't going to find the information in the book. And so there's nothing to fall back on. Of course, you can watch the videos, but most of the videos have 0 views, and I think most of the videos have 0 views because people just don't have time to go back and do that.
Where can I find your videos? On the office?
No, on YouTube. On YouTube.
Do I just search your name?
No, ECC Chem.
Oh.
Chemistry ECC. Oh, okay. It doesn't matter. I mean, still, very few views is fine, because I understand. It's just, when people are sick or they miss class, when they should take a look at that. But this is kind of critical because here I'm going to deviate. But the book is actually quite a lot from the book because chapters 8, chapters 9, and then we have a whole bunch of stuff in this that we're supposed to cover. And so let's first take a look at this here. Okay, so let me turn this on. All right, so if this is from your lab manual, and so these are the sections we're going to cover. It's going to be chapters 8, chapters 9, and then from your lab manual we have something called reactions. And these are the simplified solubility rules for common salts in water, activity series for selected elements, reactivity of metals towards water and acids, and chemical equations. And so there's some reading here. It doesn't look like that much reading there. And then we have this. It's going to jump from here to here. Net ionic equations. Looks like we have 4 pages of that. There's 6 pages of reactions up there. So net ionic equations. And then we have this. If you look at the bottom here, we have something called Chem Compact B. Chem Compact B is a chapter on chemical reactions. This is long. It's 16, over 20 pages, 23 pages worth of reading. Reading slow here. That's in addition to the chapter. Then we have another one, Chem Compact G, which deals with net ionic equations. This net ionic equation is 117 to 141, so 100 pages back. You're looking at another 50 pages worth of reading here, plus the earlier, that's like 60 pages worth of reading just from the lab manual. And so we got all this supplemental reading in the lab manual, plus chapters 8 and 9. So what I'm going to do is I'm just going to, I'm going to deviate. I'm not going to follow, because if I follow chapter 8 and then go through 9 and then come to these, it's going to take way too much time. Plus, you're supposed to, according to our notes for Chem 4, let's take a look at the chemical reactions here. So reactions 3 through 6. So I'm just going to go to that reactions 3 through 6, whatever that is. Look at reactions 1. You know, I told you there's a bit of memorization we have to do. Well, one of the things you want to start memorizing is this. You have to have this chart memorized here. These are what we call the solubility rules. I'll talk about these pretty soon, but you've got to memorize this, including the exception. There's a repetition helps you memorize that. Some people ask me about memorizing this next one. Fortunately, we don't have to memorize this because there is a pattern to it. This is the activity series. Some people ask me, do we need to memorize? No, you don't need to memorize this, but you do need to memorize some of these things from the patterns, just in general. This. And that's just so you can build some basic knowledge about chemical properties. Okay, then we have these, you know, what happens when you burn phosphorus in air? This kind of barium oxide is added to water. So there's a whole bunch of reactions here that we'll look at doing this. And then we have something called rules for determining oxidation numbers. We need to know, actually we've already been doing this, so I just didn't tell you what the rules are yet. We've been doing this all along. Okay, concentration problems we aren't doing. Net ion equations, yes, we're doing that. So we'll use a supplemental section on that here. Then I wish they put this in order here, but it's not in order, so we have to jump around. And then there's this, which is Chem Compact B, chemical reactions. So this is a chapter that's taken out. You're supposed to memorize all these types of reactions. This is probably one of the things, but we aren't, because this is, the way this is classified, I don't like the way it's classified. I don't like the way it's organized, because it's too much memorization. It depends on the instructor too. The instructors are supposed to follow the Chem 4 outline as written. You're supposed to have all these reaction types memorized. Reaction types starting with, like, say, you know, element plus element yields compound. I don't know where that is. It's earlier, a little bit earlier here. Oh, here it is. We start, you know, with combination, decomposition, element plus element yields compound, then your element plus compound, and then et cetera, et cetera. So a whole bunch of different reaction types. You know, when you look at it, it's probably over 11, 12 different types presented in here. Actually, look at the summary. This isn't the complete list here, but I'm summarizing this table. So we did this A plus B yields C, C yields A plus B, AB plus C, AB plus CB, kind of stuff. And that's that, and then a bunch of others. So we go to Chem Compact G here. Chem Compact G is longer. Here's the solubility rules. This is presented a little bit better formatting than others. It's not that hard to memorize. I've been Chem 4 many times. Usually the percentage of students who are unable to memorize this is very few. There's always students who are unable to memorize it. But most people manage that. It's not that bad. Okay, let's talk about it now. Yeah, just a whole bunch of reactions here. This is on double side. So about 60 pages out of our supplement, our additional reading. Well, let's take a look at the chapter. Chapter 8. Chapter 8, chemical reactions here. So they have a bunch here. And then go through a couple of reaction types: the single replacement type reactions, double replacement type reactions. Here, and then a summary. This is kind of similar. A lot of similarities with the, if you look at the supplement, there was the A plus B yields AB. In the supplement, this is called A plus X. Here, it doesn't matter what letters we use to represent the elements. In the supplement, they call this AB yields A plus B. The combination decomposition. And there's something called a single replacement A plus BX. These are patterns, reactivity. We can look at like this. That's chapter 8. And then chapter 9. Chapter 9 next. Chemical change in chemical.
That slide from chapter 8 for the test?
I'm sorry?
Are we going to need to know that slide from chapter 8 for the test?
The last one.
Well, you're going to need to know more than that slide, actually. Yeah, but yes. Yeah.
Are we going to go over that chapter? Oh, okay.
But it's going to be organized a little bit differently. I mean, we'll go through the first parts of the chapter because it's all the same. And then chapter 9. Chapter 9, we're dealing with, water solutions here. Talk about that. Some of this stuff, like the net ionic, I don't know. Let's see how this works. Yeah. Redox. This is the solubility rules from your book. The solubility rules are much more comprehensive in your book, much more detailed. The solubility rules in the supplement are a lot easier. We've just simplified solubility rules. So we're not going to bother memorizing these. This would be too much to memorize here. Just memorize the ones we want to do. Why do you want to memorize the solubility rules? There are certain reasons you want to memorize. Solubility just means will it dissolve in water or not? And so we're going to be drawing on information from these two chapters, plus all the information in the supplement of the discussion on chemical properties. Chemical properties, there would be chemical change or chemical reaction. Chemical change, chemical reaction, same thing. I think they just wanted to title it differently. And so let's just go back to chapter 8 here and then take a look at this. So chemical reactions. Well, evidence of a chemical reaction. Change of color. Change of color doesn't always, change of color might be dilution. Like if you add water to this, it'll change the color. And so we got to be careful. Change of color may or may not indicate a chemical change. Formation of a solid product, formation of a solid, let's say you have liquids and all of a sudden the solid appears. That's called precipitation. And if a solid appears, then obviously something happened. But the solid could appear, by evaporation. What if I evaporated all the water here? If I evaporated all the water, I'm going to be left with a solid residue on the bottom if this is tap water. Is that a chemical change or is that a physical change? Physical. That's a physical change. Just all the minerals, the salts just crystallize. That's all. And so again, we got to be careful here because sometimes that could be indicative of a physical. Formation of gas product, also that could be physical as well. If you boil water, you're going to form gas, which is called steam. Is that physical or is that a chemical? That's physical. And so we're looking for evidence. Absorption or release of heat. Sometimes it gets hot, sometimes it gets cold. That's usually an indication of a chemical change. It's hot and cold. Of course, if it starts emitting light, then it's obvious. So, we got to look at these carefully and to determine if there's actually been reaction. Because in a chemical reaction, you know, the substances do change, the atoms get rearranged, and we destroy existing compounds and replace those with new compounds. That's what happens there. Change. And so here's some stuff here. You know, this is an example. This for sure, you know, this is already colored here. Looks like it's pink. So this kind of looks like dilution, but you know, over time, do you see the color disappear? Yeah, that's got to be chemical change. We aren't really diluting it, or it looks to be a chemical change. And in fact, it is a chemical change in this case. Whatever that pink stuff is disappearing. You know? Well, it's disappearing in the sense that it's going to be replaced with some other compound. Chemical change. Now this is a case. This is not just evaporation of water. You know, when they're adding drops of this liquid in here, you see this cloudy stuff form. The cloudy stuff is actually solid because if you give this enough time, that solid will deposit on the bottom here. So this is kind of like muddy water, but this white line here. And so this is called solid formation or precipitation. You know, this is definitely evidence of chemical change here. It's precipitation. We're going to see these in lab as well. Here, this is formation of gas. You know, this is an Alka-Seltzer tab that we put in here. You see bubbles. This is bubbles of CO2 actually forming up. This is a chemical change as well. Eventually, that solid should disappear or dissolve. I shouldn't say disappear because it dissolve. Yeah, evolution of heat and light. It's obviously chemical. You got a big flame. Emission of light. Chemical change there. Luminescence. Heat, yeah. Cold packs and hot packs. Definitely chemical. Although cold packs, it turns out is a physical change. You know, some salts, when you dissolve them in water, it gets cold. And some salts, when you dissolve them in water, get hot, but the salts are still there. They're just dissolved in water. And so heat transfer, this one in particular is a physical. However, there's example of chemical ones, like when we do the Bunsen burner. When you do the Bunsen burner, there's lots of heat given off. That's for sure chemical. And so again, we just have to be cautious because sometimes this can be a physical, sometimes it can be a chemical. And so they're just certain salts, when dissolved in water, either give off heat or consume heat. We saw sodium metal. So is sodium metal stable or unstable?
No, unstable.
It's totally unstable. I mean, this is a piece of sodium. You can see it just looks like a regular metal. You don't want to touch it with your fingers because what happens if you touch it with your fingers? If your fingers are dry, it'll just start to burn. If your fingers are wet, let's say you have some sweat, what's going to happen is it's going to start to react with the water or the moisture, and it's going to get hot, and it's going to melt the sodium. Sodium only melts at 90 degrees Celsius, which is very low, less than boiling water. It's going to melt, make a little molten ball of sodium, and if it gets hot enough, it'll catch on fire, to ignite, basically. It'll catch on fire because it generates hydrogen, and hydrogen has a fairly low temperature at which it ignites, and it'll cause trouble. So this is what happens. You see that that's a little molten ball of sodium right there, and it's generating hydrogen gas. You remember the video from yesterday? The disposal of sodium metal? Did it explode or did it not explode? It exploded. This is a case where it didn't explode. Depends on the speed. You know, if a lot of energy is released in a short period of time, you get an explosion. If you can dissipate that energy slowly, then you aren't going to get explosions. Dissipate slowly. Once I was getting rid of some sodium, so I just had a few chunks of sodium, smaller than this. And so there's a little pool of water here, so I just threw it in a little pool of water. And what happened was it got hot enough that a little fireball of sodium metal came out of the sink and landed on my arm. So I had a little fireball of sodium metal on my arm and just burned, caused a burn. There. but you gotta watch out for this stuff.
Would there have been a different reaction if the sodium barrels in the video yesterday were entered into like the saltwater lake rather than the freshwater lake?
Oh, good question. Good question. It would be the same reaction. The same reaction, whether it's salt water or fresh water, it's the same. Yeah. Same. It does make a difference though for other reactions, but not for sodium. Sodium's so reactive, it'll just react with the first thing that it comes into contact with, and that would be the water. Turns out that most of the salts in saltwater ocean are less reactive than water. We're going to learn that. So in fact, that's a question I asked on the test. I've asked that on an exam, including in Chem 4. What will the sodium react with? Will it react with the salt like sodium chloride, or will it react with the water? It's a trick. I give a trick question on that. But I'll explain it to you. I'll explain it to you, but even though I explain it to you, only like 5% of the class gets it, or actually, on the first time around. The second time around, most people get it. This is the reaction. So the sodium reacts with the water. So this is Na. S stands for what? This is the H2O. H2O is a liquid. Yeah. Now, if this were salt water, we'd represent this differently. If this were salt water, we'd represent it as like NaClAQ. NaClAQ is salt water. But, what is the sodium going to react with? Is it going to react with NaCl? A lot of people say yes, it'll react with NaCl, but you'll learn that sodium doesn't react with NaCl. And so a lot of people say that there's no reaction with salt water. There's no reaction with salt water, they're going to be in big trouble, because if they think there's no reaction with salt water, yes, there's no reaction with the salt in water, but there's going to be a huge reaction with the water in salt water, which is going to cause a potential explosion. And so I do that as a trick question, but it's also a safety thing, because if you can't tell, that, then it's going to be a danger. If you're mixing chemicals together, not knowing what potentially could happen. And so that just brings up that. But I give that same exact question on a practice sheet anyway. And so what happens in this particular reaction is it generates hydrogen gas and sodium hydroxide. Well, is hydrogen gas and oxygen a stable mixture?
Wait, I'm sorry.
Is hydrogen and oxygen a stable mixture?
Just one hydrogen?
No. And so that hydrogen, if there's no oxygen present, then it's not going to explode. So if that were an anaerobic environment, we expect no explosion. We often work in anaerobic environments. I used to work in an anaerobic environment all the time. There's this gigantic box, and you have these gloves. It's overpressure, so the gloves are usually sticking out. So you push the gloves in, and you work with gloves, and you're working in this window. It looks like you're working out in space or something like that, But it's this anaerobic. Not only is it anaerobic, there's no water vapor inside there, because I have a lot of that. What was that stuff called that sucks the water out of the gas? Yeah. Well, if it's blue, it's good, but if it's red, it's bad. What was that called? We don't call it blue stuff. We would call it. Or you don't have to tell me the brand. I don't care about the brand. Just tell me what it is in general, because there's lots of them. I can get any particular brand I want. Maybe it doesn't matter. Maybe. Yeah, desiccant. I have a bunch of desiccant over there. Yeah. And so I just have a big box. Desiccant. Does probably nobody remembers the brand, the blue brand that was there. It was called Dryer Right. But it doesn't matter, because if you're never going to do chemistry, then it doesn't really matter what the brand is or that stuff. But if you're going to do chemistry, then Dryer Right is very well known. It's very common and it's cheap. That's why people use it. There's much more expensive. I used to use much more expensive stuff, and it was a hassle.
Is catheter, the desiccant?
A catheter?
No, cat litter, like litter boxes. for
Oh,
cats.
cat litter? Yeah,
Would that be-
yeah. There's desiccant in there. Yeah, it wants to dry out the, the cat excrement or poop or whatever. Well, it's got to dry that out, right? And so you need a desiccant to do that. And you want cheap stuff. The cat litter, I've looked. It is the calcium sulfate is one of the active ingredients. When I had a cat a long time ago. But there are other desiccants that people use out there too. There are other things as well that people can use. But anyway, going back to this, desiccants aren't that important. If you have limited memory space, most likely you aren't going to see a question on a test. I wouldn't ask you. If it were a regular class, though, like UCLA, we typically had a lab final. A lab final was all the practical information that you needed from the lab. There you would have seen it. But in Chem 4, we don't have a lab final. In fact, there are very few instructors here that will have a lab exam in chemistry. In biology, I guess you have those all the time. But, if you're in upper division labs at UCLA, all of them had lab finals. All of them would ask those types of questions. So just for future. All right, what we need to do is we need to do something called balancing, because atoms are neither created nor destroyed. So if we have one sodium atom here, it's got to end up over here. But this is sodium metal, this is sodium ion and sodium hydroxide, totally different. This is, even though this is H2, is this hydrogen gas? No, this is H2 and two hydrogen atoms in water. This is hydrogen gas. So this is different. And so in a chemical thing, the atoms are rearranged and they make new compounds. So that's what we see here. We got to make sure it's balanced. So we see two hydrogens here, two hydrogens, one oxygen atom. This is an unstable mixture. This is a much more stable mixture, even though this is pretty unstable too. I mean, hydrogen gas, is that very stable? No. But in an anaerobic environment, it should be pretty stable. If there's no oxygen around, is it going to explode? Well, I shouldn't say, as we'll learn in this section, we'll learn it doesn't have to be oxygen. There could be other things that could cause it to explode. So let's say we had no oxygen around, but we had some perchlorate around, then you better bet it can explode. In fact, perchlorate is much more powerful, what we call an oxidizer. Oxygen is an oxidizer. When we live in an aerobic environment, we've got to worry about oxidation. You worry about oxidation of metals. Oxidation of metals causes billions of dollars of loss and damage every year, And so oxidation of metals, like iron, is huge. Of course, we can't just blanket everything with anaerobic gas. It'd be too expensive. But that's what they do. When they put the platinum and iridium in that bell jar in France, you better bet they're surrounding that not with air, but with a special gas, like argon or helium or something like that, to protect it. Anyway, this turns out to be unstable, and this is much more stable. And so energy is neither created nor destroyed. So if we're going from something that's unstable, high energy, to something that's low energy, all that excess energy has to go somewhere. It doesn't disappear. And so that's why they put heat here. But oftentimes we'll ignore this, and we won't even write heat here. There's definitely going to be an energy exchange. And so here, this is optional. And so typically it's written like this. But this is this balanced? That is, does this look okay? That is one sodium, two hydrogens. Yeah, except there's one extra hydrogen atom. If there's one extra hydrogen atom, where did it come from? You can't just add an H over here and then everything's okay, because we only mix these two things together. And
And so what we have to do is we have to change these guys. We have to change the number. These are called the coefficients. We always change the coefficients. We never change the subscript. So for example, I want 3 hydrogens here, right? And so can I change this to H3O? No, I can't, because all of a sudden that's no longer water, right? That's gonna be something else. And so what we have to do is we'll change the number here. And so if I double these, let's say 2 sodiums, 2 waters, and then leave this as 1, and double this one, then it works out, because now I have 2 sodiums, 4 hydrogens, 2 and 2 is 4 hydrogens, and 2 oxygens, 2 oxygens. So it works out. Do you guys see that? That's called balancing. And so this is called a balanced chemical equation or balanced chemical reaction. And we balance it by changing these, the coefficients. We also need the state: solid, liquid, gas, aqueous. We want the state. When looking at the states, this sodium, what type of structure? The sodium form molecules? No, sodium doesn't form. Sodium is going to form a metallic lattice. And I showed metallic lattices a long time ago. Water is a liquid. We saw the simulations of water. Water is molecular. It's a molecular liquid. Hydrogen's a gas, so we're going to have H2 molecules in the gaseous state. What about this guy here, sodium hydroxide, AQ? We see there. What this is this. We're going to form sodium hydroxide. You know, most salts liquids, solids, or gases? Most salts are solid. And what is a salt? A salt is typically an ionic compound that's not an acid. It's a metal plus a non-metal. So we have phosphate salts, we have chloride salts, we have lots of different salts. It turns out that this salt, if there's water around, will dissolve in water. And so this is what we call a soluble salt. How do I know it's a soluble salt? Well, it turns out that practically all sodium salts are soluble. How do I know that? Oh, I memorized the solubility. So we can figure out that this is going to be AQ. Because there's water around. There's water around, that salt will dissolve. Now, some salts will not dissolve in water. So for example, calcium carbonate. Will that salt dissolve in water? Calcium carbonate is also called limestone. Does limestone dissolve in water? Calcium carbonate makes the shells for animals. Do those shells dissolve in water? No. And so if they did, the shells would be pretty worthless for the animals. And so those do not dissolve, and those we would write solid here, because even if there's water present, you aren't going to expect animal shells to dissolve in water. Okay, how did I know that? Well, I memorized the solubility rules. But yeah, of course you can Google the solubility rules, but if you want to talk, you know, and let's say you're giving a scientific presentation, you know, you're giving a scientific presentation to an audience like this, and you tell the audience, wait a minute, let me Google that, you know, what are they going to think? They're going to lose all respect, you know. And so there's a certain amount of base knowledge you have to have memorized. Of course, there's some things that, you know, you aren't going to be expected to have memorized, you know. And that you can say, well, I don't know, you know, I would have to look that up, you know, basically, or to have to find that information. That's fine, but there's like basic knowledge that, you know, you should have down in order to talk science, because when you talk science with other scientists, you know, other scientists will get annoyed if you have very little basic knowledge, you know, in talking. And other scientists will, you know, it depends. You know, some scientists are nice, some scientists aren't so nice. Do's and don'ts. They're like people, like everybody else. They're all kinds of people. Do's and don'ts of balancing a chemical equation. Of course, we don't change the subscript. Only change the coefficient. That's it. That's what I'd write for that. Writing and balancing a chemical equation. Now let's skip this. This approach, skip that. All right, balance the equation for the reaction of solid phosphorus pentachloride with liquid water, yielding aqueous solutions of phosphoric acid and hydrochloric acid. So here, this is kind of nice because they tell us what we have initially, and then they tell us what we're going to form. So our job is just to write down the formulas and balance it. And so this one's not so bad. And so let's go ahead and do this one, and then we'll go through some tips for balancing these down. So solid phosphorus pentachloride, what's the formula for that? P PO4 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 Cl PO4 Cl 4. Okay. PO4 Cl5. I see some.
PO4 5 or CL4.
Okay, PO4 5 Cl3.
Yeah.
Are we good? Anybody have something different? PCl5. Anybody else have a different? So, okay, well, let's just take a quick, how many people got this? Or one? Oh, this one? This one? All right, we'll just go with the majority. The majority have picked PCl5. Of course, we could Google it and then see, and then confirmation, but you can't Google everything, and then you got to watch out. Watch out, because once I went to Yahoo Answers because I was just curious what Yahoo Answers would give, and the students voted, just like we voted here. The people voted for the best answer on Yahoo Answers, and it was ridiculous. The answer was awful. It was 100% wrong, yet it was voted the best answer. So be careful, because the people who are voting may know just as little as the questioner there. And so even though this is why, when scientists do peer review, they try to do peer review with the experts in the field, not just random people picked off the street. But anyway, it looks like you guys have got it right. PCl5 is correct. Liquid water. So this is solid, plus H2O liquid. Yields, okay, this is yields, this little arrow here. Yields, aqueous solutions of phosphoric acid. Phosphoric acid. Good. H3PO4, that was quick. That's the way it should be. That's good. H3PO4 aqueous, and hydrochloric acid. HCl. Good. Phosphoric acid and hydrochloric acid are very common acids. So those are good to have. Especially hydrochloric acid. Hydrochloric acid is used so much. They use this in pools. Do you know what they call it though? They don't call it hydrochloric acid. I don't know why. Probably because the name. The name sounds so bad. You know what they call it? Muriatic acid. Muriatic acid is hydrochloric acid, but muriatic, that sounds even worse to me. Muriatic acid, I have no idea what they're talking about. Hydrochloric, I know. Not bad. Okay, so what we need to do is we need to balance it. And so the way we balance it is, usually you try to leave the simplest ones for last. But, it's hard to say, so we'll probably start off with P. So we have 1P, do you see that? 1P, 1P. We're good. Over here we have 5 Cl. over here we only have 1, so what we'll do is we'll just change the coefficient to 5 here. Now, I don't want to touch this one, or this one. The only one I want to touch is this one, right? Because if I touch this one, or this one, it just screwed up what I just did. And then I'm going in circles. And so now let's count out the hydrogens. 5 hydrogens plus 3 hydrogens gives me 8 hydrogens. So if I do 4H2O, hopefully it works out, so I get 8 hydrogens. But that's going to give me how many oxygens? 4, and then I have 4 oxygens, and this is worked out. Good. And so 1 PCl, 4, 1, 5. So it worked out. All right, when we interpret we have 2 levels. When we read this, actually more than 2 levels. This could be 2 molecules of hydrogen, 1 molecule of oxygen yields 2 molecules of water. Or this could be 2 dozen hydrogen molecules plus 1 dozen oxygen molecules yields 2 dozen water molecules. This is what we call balanced chemical equation. Or we could say 2 moles of water molecules plus 1 mole of oxygen yields 2 moles of water. Here, this one would have to be at the dozen. For example, if we have 1 dozen water, we could have a half dozen oxygen. Is a half dozen oxygen okay? Sure. And then that produces 1 dozen water. So this would be what we call the mole level. So if we have 1 mole of hydrogen, we could have a half mole of oxygen, no big deal. That's going to yield. But this would not be at the particulate level, because at the particulate level, is it possible to have a half an oxygen molecule? No. And so some people say fractions are not, fractions are fine. We can have fractions, no problem. However, we cannot have a fraction of a molecule. We can have a fraction of a mole, we can have a fraction of a dozen, we can have fractions. And so some books want no fractions, but when you get into chemistry, we need fractions. We have to have fractions because sometimes we want to know how much energy is required to produce a mole of water. How much energy is required to produce a mole of water? Or how much energy is released when we produce a mole of water? So will energy be consumed in this reaction, or will energy be released in this reaction? How can you tell? You should be able to tell me. Is this, when energy is released, what do we call it?
Exothermic.
Good. And when energy is consumed, what do we call it? Endothermic. So is this an exothermic reaction or endothermic reaction? You should be able to tell me. Is endo consumed or released? Consumed. Then that's wrong. That's wrong because how do I know? I look at this. Is this a stable mixture or unstable? A mixture of hydrogen gas and oxygen gas. Is that stable? Do you want that in your closet, sitting in your closet? A mix. You probably don't want water sitting in your closet too, because maybe you get mold or something like that. But you know, if you had to pick, what would you pick? Having a container of hydrogen and oxygen gas, or having a container of water and then just forgetting about it? What would be safer? Water. And so that means that hydrogen and oxygen gas are unstable, high energy. Water is stable, low energy. So we're going from high energy to low energy. What happened to all that excess energy? It's got to go somewhere. It's called exothermic. This is an exothermic reaction. And so, but we aren't showing it. This would be plus heat. If this were endothermic, we put the plus heat on the opposite side here, showing that energy has to be put into this. But typically when we're doing this, we want to know how much heat per mole of water, not how much heat per 2 moles of water, because 2 moles of water is going to produce twice as much heat as 1 mole of water, right? Let's say you melt 1 pound of ice. To melt 2 pounds of ice, is that going to take twice as much heat? Yeah, it's going to take twice as much heat to melt 2 pounds versus 1 pound of ice. And so these are the types of things. Anyway, so sometimes we use fractions so that we know the energy associated per mole of water. Because normally, do we work with particulate level? If we work with particulate level, what else do we need to know about this equation up here? if we're working at particulate level, what else would we want to know about this equation up here? We need to know the isotope. What isotopes of hydrogen are we dealing with? Is this H1H1? Is this H1H2? H2H2? H2H1? Or maybe even tritium, H3H3? Or H1H3? Right? That's what we want to know at the particulate level. So we don't really work at the particulate level unless you're like an atomic physicist or atomic chemist kind of thing. And so typically we'll work at not the particulate level, typically we'll work at the dozen level or the mole level. We'll typically work at the mole level. And so, do you know 1 mole of hydrogen gas is about 25 liters? Half a mole of oxygen gas is half that size, about 12.5 liters. We can work at the mole level. This is at the particulate level, so if I'm dealing with a particulate level, I'm very interested in what isotopes. Because how many different oxygen molecules are there? A lot. And so I want to know which of these, that's going to tell me what I form over here. Usually it's random because, I shouldn't say it's usually random. It depends. A lot of people work with isotopically pure. You know, what they do is they get a sample of the stuff and then just purify it. That is, for example, they don't want a mixture. They only want one. It's going to be very expensive. And so when they're doing, fusion, have you ever heard of fusion? Fusion is what the sun does. They fuse hydrogen atoms together to form helium and generate a lot of energy. It's the sun's fusion. Well, people are trying to mimic that on Earth. Do you think they care about what isotopes they're using in fusion? Even though they're working with larger, yes, they do care. I mean, because it makes a big difference. They can't use H1. Does H1 have any neutrons? They're trying to make helium. If they're trying to make helium, they gotta use at least H2. And so they're gonna get rid of all the H1. Just use H2. And so if you're working at that kind of level, then we care about that, but we don't care about that because we're just gonna do the average. Always care. And so, yes, this is a particulate level, but what we're doing is we're doing a mole. We're not just taking 2, we're taking 2 moles. 2 moles would be what? How many of these molecules are we looking at for 2 moles? Those approximately. Yeah. How many molecules? If we're dealing with 2 moles of hydrogen, how many molecules are we looking at? Times 2. So 12 times 10 to the 23rd molecules. 12 times 10 to the 23rd molecules of hydrogen. 6 times 10 to the 23rd molecules of O2. This is going to produce about 12 times 10 to the 23rd molecules of H2O. So we're dealing with huge. In other words, I said 600 million trillion, but that would be, 12 would be 1 billion trillion hydrogen molecules, 600 million trillion oxygen. This is about a dozen. A dozen's still way too small. 2 dozen, 1 dozen, 2 dozen. That wouldn't even be 1 drop of water. How many water molecules are there in a drop of water? Well, let's do a quick calculation for this as a review for dimensional analysis. We need to know the size of the drop. And I didn't give you your experiment 2 back, but does anybody remember about the size of a drop of water in milliliters? I looked at most people got around 0.04 milliliters for 1 drop of water. I think most people got 0.04. But it's getting too detailed, and so typically what we say is a drop of water is about 0.05 milliliters. So we're going to just assume 1 drop is 0.05 milliliters. This is water. Now, if you have ammonia cleaner, then the drop is a lot smaller. If you have some syrup stuff, the drop is bigger. It depends on, you know, what's in it, in the drop of water. And so this is a very quick calculation here, because 1 drop of water is 0.05 milliliters. So let's start off with 1 drop and then of H2O. And then what we're going to say is that they're going to be 0.05 milliliters per drop for the water. Okay, then where are we going to go for milliliters? We need to get rid of milliliters, so where should we go next? To grams. And what do you know about water? The relationship between milliliters and grams of water? It's 1 gram per milliliter, or give me as precise. 1.0. Yeah, 1.0 grams per milliliter. This is the density of water, so everybody should have that memorized. And then milliliters cancel, drops. Now we have grams of water. Where can we go from grams of water? Grams to moles, good. You know, this is new, but now when we have something, you know, earlier we couldn't go too many. And so we're adding more branches. More branches is more paths that we can take through the jungle. The jungle is problem solving, because problem solving sometimes is like a jungle. So many different paths, which one do you take? And so you just try different paths. That's the problem-solving method requires some persistence. You know, you don't want to give up. You know, if you're lost in the jungle, you don't give up. You just try different paths. And so, what's the relationship between grams and moles of water? You might remember this from yesterday. What was it? What was the number? No, not that one.
Wasn't it 60 grams per every?
No, not that one. It should be in your notes. It's 18.02. We calculated that was the average from yesterday. Do you remember this number? 18.02 grams per mole? Okay, now give me the 6.02. What was it? Because now we want to get rid of moles. There are lots of different ways we can go from moles, but the most convenient would be 6.022 molecules per mole of molecules. And so molecules per mole of molecules. So I told you it was a quick calculation, so we wanted to go ahead and calculate. 0.05 divided by 18.02 times 6.022 times 10 to the 23rd. 1.6 times 10 to the 23rd. So this is going to be 1, 6. Now I'm going to go 21 times. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That was 1,000, million, billion, trillion, 1,000, million, billion. Is that right? Screw that up. 20 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I got 20 zeros. So this is 1,000, 100,000, or million. 10 to the 6th is million, 10 to the 9th is billion. Oh, here we go, trillion. Then we'll go 1,000, million, billion. And so, that's still weird. Maybe I screwed it up earlier. But this would be about 1.6 billion trillion water molecules, right? In 1 drop of water. Assuming I didn't screw it up.
Just to clarify, the 1 mole divided by 18.02 grams, that's another way of saying that 1 mole worth of water molecules is equivalent to 18.02 grams. Okay.
I screwed it up, possibly. What did that? I think I screwed it up. Maybe I should fix it right now. What's Avogadro's number? 6.022 times 23rd, right? So I'm going to move the decimal 23 over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Then figure it out. So this is 1,000, million, billion, trillion. This will be 1,000, million, billion. Shoot, no wonder. Avogadro's number is not 602 million trillion. Avogadro's number is 602 billion trillion. Sorry, this is a billion trillion. I just realized that because this comes out to 1.6 billion trillion. There are 1.6 billion trillion water molecules in a drop. In 18 milliliters, there'd be 602 billion trillion water molecules. But anyway, that's a lot of water molecules, so even a dozen's too small, so we use a little mole. Mole would be 18 milliliters. And so we're going to look at some types of reactions here. But before we do that, I don't particularly like this classification scheme because we have lots of different combination reactions. And so we have combination reactions and we have a lot of subcategories of combination reactions. And so I'm going to start deviating from the book, but since I'm going to deviate from the book, I might as well talk about most of this stuff at once. And so now I'm going to combine these chapters, but before I do that, I'm going to jump to chapter 10 because we have to look. You know, I've been talking about structures. You guys know about lattice structures, right? Molecules, that kind of stuff. You know, you guys know about the structure of gases, right? Like this, right? That's not a big deal. But we haven't really talked about the structure of solutions, these mixtures. That we have to talk about now. And so I'm going to talk about that. Oops, I jumped ahead too far. This is chapter 10. I need to go to chapter 9. This one. And so we're going to jump to chapter 9. I'm going to jump to chapter 9 because I want to talk about this. I'm sorry?
Like sometimes, like you miss it.
Yeah, don't blink. Sodium solid. When you visualize sodium solid, what do you visualize? This is what I visualize. I visualize a metallic, what do you call this? A metallic lattice, you know? Solid sodium is going to have a whole bunch of sodium ions. Sodium ions, is that correct? Or sodium atoms? Atoms. Because there's this. Have you heard of, your book is going to talk about this. Even though they're the same element, their behavior is totally different. Totally different behavior. So your book calls this the Dr. Jekyll and Mr. Hyde. How do you spell Dr. Jekyll? C-K? L-E?
Oh, J-E-K-Y-L-L, sorry.
J-E?
K-Y-L-L.
Okay, thanks.
2 L's, yeah.
Dr. Jekyll and Mr. Hyde.
H-Y.
H-Y-D-E?
Yep.
E? Okay.
Yeah.
All right, and so which one was the stable one? Which one was the monster? Dr. Jekyll is the stable one, right? And so which one should we assign? The ion stable or the metal stable? The ion stable. And then Mr. Hyde was the unstable one, so that should be the metal there. And so even though they're the same element, their behavior is totally different because of the charge. And we see that all the time. Remember the chlorine? You know, what is a happy charge for chlorine? -1. What's an unhappy charge for chlorine? That's a terribly unhappy charge for chlorine.
About 4.
Plus, yes, it is, +7. In fact, that's the unhappiest chlorine is ever going to. Oh, well, actually, it could get even unhappier. You know, but it's going to be very dangerous stuff. You know, very dangerous. Charge is everything. You know, because you know what are chemists most interested in? Chemists are well. What force of nature is chemists most interested
Force of
in?
attraction.
Force of gravitational attraction. Oh,
Electromagnetic.
what did they call it? In the book, they called it. Do you remember what they called it? Our book, what Procolici called it?
I know what you're talking about.
Like chapter 1. Chapter 1. Remember the pith balls? The pith balls from chapter 1? Is that like kindergarten stuff, or is that like not kindergarten? It's like highly advanced. Was it chapter 1? I don't even remember. Chapter 1. Maybe it's chapter 2. Yeah, chapter 2, sorry. Chapter 2 like kindergarten stuff, or is chapter 2 still current? Hopefully this is like kindergarten stuff. Yeah, that's what they called it. That's what he called it. Electrostatic. Well, we're interested in electrostatic forces. I jumped into it a little bit more because I talked about Coulomb's law. Coulomb's law is, you know, the behavior of these electrostatic. Chemists are most interested. This is why charge is so important, because charge is like this. This is the Dr. Jekyll and Mr. Hyde. Because charge makes all the difference in the world. This is why, to me, I get so frustrated when people do not write the charge. Like people will write like chloride with just Cl, no charge on there, and then I think
That's chlorine.
yeah, that's chlorine, but I asked for chloride and they wrote chlorine, and it's like, oh my god. It makes a world of difference. And so, of course, it's going to make a world of difference. It could mean the difference between an attraction and a repulsion. Is that a big difference?
Yes.
Yeah, it's a huge difference. Why people don't care is beyond me. The charge is so important. This is why on the test I asked you, and I asked you the same exact question as on the practice test. Why? Because it's so dang important. And that is, the most important force in chemistry is going to be the electrical forces. I know, okay, I know it was the same exact question, but you know, I don't care. It's an important question. Well, anyway, so we visualize sodium as being a solid lattice like this. We call this a metallic lattice. And then, what do we call that? The molecular formula? The empirical formula? What is that? It's empirical. Obviously, we're going to. The crystal, does it have a beginning and end? Not really. So if we have 2 of them, that means we have twice as much. You know? And so this is 1 mole. You know about how much does 1 mole of sodium weigh?
Wait, what, sorry?
Do you know about how much 1 mole of sodium weighs? 23 grams. So if this is 2 moles, well, it's not 23 grams, it'd be 46 grams. So we need about 46 grams of sodium here. And then what we're going to do is we're going to react this with water. We need 2 moles of liquid water. Well, do you know 1 mole of water, about how much it weighs? 18 grams. So 2 moles would need 36 grams of water. And so here we're gonna have about 46 grams of sodium, and then here we're gonna have 36 grams of water. 36 grams, how much do I need to measure out in the grad cylinder to get 36 grams of water? 36 milliliters. So I'm gonna have about 36 milliliters of water here. Okay, and then this is going to form hydrogen gas and 2 sodium hydroxides, AQ. All right, and so the hydrogen gas, we just visualize this. It turns out 1 mole of hydrogen gas is about 25 liters. We haven't, did we do Charles' law already? Yeah.
Yes.
We did Charles' law, but we didn't talk about, we gotta come back to gases. And so there's gonna be a second gas chapter. In the second gas chapter, we're gonna look. You know, if I have 602 billion trillion hydrogen molecules in here, how much space does that take? Well, it takes only about 25 liters to put 602 billion trillion water molecules at 1 bar pressure in 25 degrees C. And then the sodium hydroxide. Well, the sodium hydroxide is going to be in this. This is going to be about 36 milliliters, let's say. Usually we add more water. You know, we'll just add in more water. 36 is the minimum. If we put in 36, there'd be no water left. And so typically we add plus lots of extra water. If I could just put in 36 milliliters of water, all that water would be consumed in this reaction. And there would be no water left. And so what I need to do is I need to add extra water. This extra water, this is what we call excess. So I'm taking sodium, because what I want to do is I want to make sure all the sodium reacts. I don't want any leftover sodium, because leftover sodium is dangerous. However, if I have leftover water, is leftover water dangerous?
Yeah.
No, so leftover water is no problem. And so what we're going to do is we're going to add excess water. This is what we call the we're going to see this in chapter 10. Stoichiometry just refers to the amounts. So this is what we call the stoichiometric amount, and we're going to put in more. So plus extra water. That extra water is going to be here. 36 milliliters is no longer there. It's been consumed. And so this is from the excess water. The excess water, now we have sodium hydroxide in the water. Now sodium hydroxide is normally in the pure form. What does sodium hydroxide look like? Well, let's look over here. Pure sodium hydroxide you can buy in the supermarket. Did you know that? I was at the supermarket. Actually, no, let me take that back. You can buy it at the supermarket, but I wasn't at the supermarket. I was at Orchard. And Orchard Supply, you know, Orchard Supply was going out of business, so I went there because I thought I'd be able to get a good price. And it was a good price. It was like only 10% off or something like that. But
It's not good.
do you know what section I was in? It's not good, yeah.
That's tax 30%.
Yeah.
I do
Yeah.
Oh, really? Are you there?
No,
Oh,
no,
okay.
I'm just saying, like, anything that's over 50% isn't too good.
Yeah.
Anything under is no.
Okay. Well, anyway,
Whoa.
this was, you know what I was looking for?
No.
I was looking for drain cleaner. And have you heard of Red Devil Lye, this brand, or Lye, or drain cleaner? Drain cleaner, sodium hydroxide works great as a drain cleaner because sodium hydroxide, what it does is you have fat molecules typically clogging your drain, and the sodium hydroxide will break apart the fat molecules pretty well and allow it to drain. They also use sodium hydroxide to make soap, you know, or potassium hydroxide, sodium hydroxide. You take fats and then you break those apart and you can make soap out of that, right? And so maybe there's some oil in the drain. I don't know what was clogging it, but sodium hydroxide is pretty good because it breaks apart lots of things. Lime. And so I was looking for this, but you know, it was pure, and it's a white solid. And this we call salt. And this salt happens to be soluble in water. Being soluble in water just means it dissolves. But let's take a look at this. What type of structure do you expect sodium hydroxide to have?
Lattice.
Ionic lattice structure, because it's made up of 2 ions. Can you tell me the ions it's made up of? Na plus and
OH minus.
OH minus. hence the name. Sodium ions and hydroxide ions make sodium hydroxide. This should form an ionic lattice. So it should have a lattice structure. And so, actually, let's take a look at what that lattice looks like. And so NaOH, we call it crystal structure when we want to look at the lattice itself. This is not sodium hydroxide, it's some crystal lattice. It's sodium chloride. Oh, actually, that's break time. Well, let me do the lattice. Can you see the lattice here? Okay. What are the sodiums? Actually, this doesn't quite look like sodium, but maybe it is. What are the sodiums? The purple or the red? Purple. Purple. What are the hydroxides?
The red
Red and the gray. Red's oxygen. So this has got to be sodium. So it packs together in a lattice like this. Do you see any sodium hydroxide molecules in there?
Yeah. Wait. Oh.
That is, well, which one of these is the molecule? Is it this one and this one? Or is it this one and this one? Or is it this one and that one? Which one of these is the molecule? Well, there is no discrete molecular unit, so it doesn't form molecules. So this is what we call a ionic lattice. Well, what happens if you take this ionic lattice and dissolve it in water? What happens is the lattice gets broken apart, and so the ions get separated. And so I don't think we have this for sodium hydroxide, but we have this for sodium chloride. Actually, let's well, I'm going to stop here and we'll take our break and then